All right, guys. So, as you know, we're studying light, and here I have listed all of the properties of light. Unfortunately, we're probably not going to get to discuss all of them this year, but you should totally look into them because some of them are really cool, like polarization, for example, really cool effect. Anyhow, first we're going to start with a little bit of review, like reflection. Now, you learned a little bit about reflection already, and what do we got going here? Here you can see there's some source. This is my source, and there's light coming in. All of these rays incident to the mirror. Now, we know mirrors reflect, which means there's an image on the other side of the mirror. Now, that image is where all of those light rays would converge if I were to trace those reflected rays. Let's look at that one more time. These are the incident rays, and we know there's a reflection because we've seen that. Now, if I trace every one of these reflected rays, they come all intersecting at some point. That is where my image, this virtual image, will show us. Now, we know things about plane mirrors. This is a plane mirror or a specular reflection. We'll talk about that again. And we know if I am, off the screen, if I am 5'9" tall, that means my reflection is 5 feet 9 inches tall. I know if I am some distance away from the mirror, my reflection is that same distance on the other side of the mirror, provided that mirror is a flat plane mirror. We all know how mirrors work. We've lived here a long time. We also know that this person inside of the mirror is not a real person. They are a virtual image, meaning I can't touch them. They are imaginary. They live on the other side of the mirror. I can't get them. So dogs are confused by this, and if you've ever been in any restaurant in your entire life, most restaurants have a whole mirrored wall. Why would they have a whole mirrored wall, do you ask, Mr. Rose? Well, it is because it makes the appearance from the outside of either being twice as big, or if there are a lot of people, having twice as many people. So now you know something. Now, we know that if you stand further away, your image looks much smaller. Well, why is that? Because it's further away. That makes sense. Things that are far away look smaller. So your reflection on the other side looks smaller. But no matter what, those two images are the same size. Now, if I take a plane mirror, right close up to my face, obviously my whole body doesn't fit in that mirror. That's all we're saying here. Now, reflection vocabulary. You can't see the vocabulary because I'm in the way. A real image. A real image is an image that is made from real light rays that are converging at some point. That is called a focal length, and that is real. Real images can be projected onto a screen. So that means light rays are coming into like maybe a curved mirror and getting reflected in some other fashion, so they are projected onto a screen. Mirrors are harder to deal with that than, say, lenses. But real images are those that can be reflected as opposed to a virtual image, which is not real, cannot be projected. The image only seems to be there. Now, ask yourself this. The frog that we saw out of my little demonstration last time, is that a real image or a virtual image? I don't know. You should know. Figure it out. Now, we also have done this before, and it confuses us when we're kids. I raise my right hand and my reflection raises its left hand. Also, if you ever noticed on police cars and ambulances, the ambulance on the front is written backwards. Well, why is that? Because if I'm the driver and I'm driving my car and I look in the mirror, then it's right side up in my reflection, so I can read the word ambulance in the reflection. You should try it. See this word ambulance? Take a mirror to it. See if it is the right way. Now, if you hold the mirror that way, it's going to be hard to see. Therefore, you can, check it out. Now, reflection. These are going to be some kind of lame animations as well. There's the mirror on the bottom. Then we have, remember that line, that perpendicular line, that's the normal line. That is an imaginary line that we draw, so we can figure out things about our mirror. Now here I have this ray coming in, which you call the incident ray. So that ray comes in, bam, and bounces off my mirror. So it is reflected off of my mirror. That is the reflected ray. Now, the angle of incidence that I have there, that is the angle between the incident ray and the normal, is equal to the angle of reflection. Those are always measured with the normal on a specular or plane reflection, as well as a diffuse reflection, which we can get to momentarily. These angles over here, they're nothing, and I'll show you why they're nothing in a moment. Now, an easier way to say this angle of reflection is equal to angle of incidence, or flip that, angle of incidence is equal to angle of reflection, is just by saying whatever the angle is that comes in, it is the same angle that it goes out. Angle in equals angle out. That is the law of reflection all of the time. Now, regular reflection or specular reflection is nice and easy. Diffuse reflection is like a dull surface, or if I've ever looked at my reflection in like a piece of aluminum foil, I'm not as pretty as when I look at my reflection in a mirror, because that is not all as smooth and as flat. So that is diffuse reflection. And diffuse reflection is the exact same thing, angle in equals angle out, except it's hitting the surface in all these different ways. So that's why we always measure with the normal. So this one right here, the normal line goes way up right in that direction, and the angles are really small. So that's why we always measure the angle with the normal and not with the plane. Otherwise, it would be a little bit confusing. Now, quick spot about curved mirrors, because I know you read a little about them. Now, curved mirrors are tricky. One, there is a mirror on a car on the other side of the driver's side, the passenger side of the car, that says objects in mirror are closer than they appear. That's because it's bent in such a way, it's either a concave or a convex mirror. It is, think about it, it is a convex mirror, so I get a bigger angle. I get a bigger viewing angle, so I can see more, but it makes the objects look different. Now, mirrors in some stores by mistake actually make you look either bigger or smaller. It may not actually be by mistake. In fact, as you can see in my picture right here, this was a mirror on Shark Tank that was called the skinny mirror. And what the skinny mirror did is sorry, I'm standing up too early, is it catered to specific people, like those people who wanted to think that they were skinnier and feel better about themselves. So I get all dressed in my pretty clothes, and I'm like, oh, look at me in my mirror. I'm looking all good in my mirror. Except that was a lie. It was a lying mirror. What that mirror was, it was curved. It was a little bit curved in one way, probably a little bit concave. Concave means it's kind of caving in, such that when you were there, when you were in front of the mirror, it was ever so slightly, you looked a little bit taller and a little bit skinnier. Now, that's not the only types that happen. Sometimes when I go to the gym, I gotta get my flex on. I just hit my hand and that hurt because, I broke my hand. Anyway, and, a lot of guys at the gym do this. What's up? Yeah, people at the gym do this. And they want to see themselves flexing in the mirror. Now, those mirrors also are specifically designed to make you look maybe just a little bit shorter, but a little bit bigger. And that caters to another specific type of person. Now, these don't always work. And if you're worried, like, oh my God, are these one of those mirrors? There's an easy way to tell. They're funhouse mirrors. Now, sometimes a mirror just under the weight of gravity does get a little bit deformed. And some mirrors are cheaply built, so they're not done intentionally. If you ever think you're standing in front of one of these mirrors, just stand there and do this. Go up and down and up and down. And if your body starts to look a little different, it's a mirror that doesn't look very good. I'm sorry, that doesn't work very well. So that's my little spot about curved mirrors. Now, got to ask you a couple of questions. Question number 1. You can't see, I'll read it. When sunlight falls on a water surface, which of the following is going to occur? There's my sunlight. There's the surface. Is the air going to be reflected? Is the sunlight going to be reflected back into the air? Is it going to refract, whatever the heck that means, refract into the water? Is it going to be absorbed and turned into heat in that water? Well, if you think about this, then you are absolutely correct. It is 1, it is 2, it is all 3 things. Yes, all of the above. Next question. Little Sharky, he says, again, my face is in the way, when hunting people above the water, what? Oh, hunting people above the water, what's happening? When hunting people above the water, there's Sharky hunting people above the water. Should you aim your spear directly at that person? Well, do you agree? Of course you should aim your spear directly at that person. Maybe not, because that person's actually located somewhere else. Or no, because the size of an object changes when you're put up underwater or above water. Well, obviously this is not all of the above, just bam, question number 2, and that is because of refraction. Now, what is refraction? All of these things are refraction. Actually, this guy's a little dispersion. A rainbow is a little bit dispersion. That is definitely refraction. Right there, that part is refraction. And the light bending is refraction. Eventually, by the way, we will answer why is the sky blue. I know you want to know that answer too. So let's move on to refraction. Refraction specifically is talking about how much light, in this case, we're only talking about light. Again, all waves do this, but we're only talking about light. How much light will speed up and or slow down when it changes mediums. And the index of refraction is called, I like to call it, optical density. In other words, how much it's going to be affected. We're going to explain. Oh, here's an equation. N is the index of refraction, and that refers to the speed of light in a vacuum. Remember, a vacuum is just something where there's no air, compared to the speed of light in a medium, which is why we have C, that never changes, over V, how fast it's going in the medium. We'll get into that equation. This is actually an easier equation than the one we're going to show you, but this is an important one. And the index of refraction of any medium is the speed of light, constant, 3 times 10 to the 8th meters per second, divided by the speed of light in that medium. Now, what is refraction? Well, refraction is when waves blank or slow down due to traveling in a different medium. Well, if it is blank or slow down, that is going to speed up or slow down due to traveling in a different medium. Oh, I already gave the answer. Medium. A medium is something that the waves will travel through when a pen is placed in water and it looks like this. Ah! That pencil is broken! Ah! That pencil is broken too! Don't worry, those pencils are not broken, plus those are just pictures I stole from the internet. But you can do that. You can take a glass of water, put a pencil in it, you can go, ah! That pencil is broken all for yourself. Now, in this case, the light rays travel into the air, into water. Water is more optically dense than the air. Thus, the light wave is bent, right there, bent. Oops. And the two mediums in this example are air and water. Everyone always forgets about air as a medium, but yeah, there's definitely air here. Air is a medium. All right, so now I want you to try this. Okay, I want you to try this. Get yourself a sparkly glass like so, and get yourself a coin like so. Put that coin in the glass, and then put the glass on a table. Now, I can't do that because then you're going to see. And when you put the glass on the table, I can see the coin and start stepping back until I just can't see the coin. So in other words, looks just like that. Now, what you're going to do is take some water like I have here. Remember, I just can't see the coin. I'm going to start pouring that water in. Pour, 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 pour. Don't move, don't move, don't move, don't move, don't move. I can't hold the glass anymore because my hand is too heavy. I'm sorry, because my hand is hurt. And all of a sudden, you're going to get to see the coin. And it's super exciting. One of the best demonstrations you can do at your house right now. Anyhow, now that you've done that demonstration, come back. This is refraction. As long as that coin didn't move, you couldn't see the coin. Now, the water makes the light bend such that you can see the coin. It's a pretty cool party trick. So, anytime light is going from one medium to another, like air to glass, the light is going to bend. It goes from one medium to another. So, here we have the light traveling from air to glass, and it bends. Now, I'll show you this too in a minute. If we have air to glass, again, this is called the incident ray. Incident's just a fancy word for incoming. This looks just like the one. Now, that is the normal. Remember, the normal is always an imaginary line, just like the normal force that we drew, perpendicular to the to the surface. Now, that as it slows down, this is the angle of incidence, just like before. Now, as it slows down, this is the refracted ray. Now, this is what people make a mistake. We always measure with the normal. So the angle of refraction is still measured with the normal. Now, from water to air is totally different. Now, it's not actually totally different. It's just the exact opposite. Now, if I have light going from the water, that's the incident ray, into the air. Now, this is upside down, but you can imagine, like, if you're in a pool and you're looking out of water, up from the water into the air, then you are going from the water to the air. So now it is going to bend away from the normal. So this is the incident ray, and this is the incident angle and reflected angle. And the light bends away from the normal. Now, sometimes it gets tricky, and this would be the hardest example. I'm going to walk you through one of these. This is going from, say, air into a medium like glass, and then back into air. Now I have a normal line drawn here and a normal line drawn here. So what's going on here is as I go from air into the glass, it bends towards the normal because that light slows down into the more dense medium. Now when it comes out and bends away from the normal, it speeds up and bends away, gets faster. So internally it's going the slowest, outside it's going the fastest. Waves always slow down when they enter a medium of a thicker optical density. Now, if it was straight up and down, that's what this one is showing. Like if I was shining a flashlight straight perpendicular, it doesn't matter which direction, It's still going to speed up or slow down, but we can't measure the angle because it doesn't actually bend. All right. So this is just a summary. When we speak of more dense or less dense, we're really referring to, again, that index of refraction. How much light waves speed up or slow down as they enter a medium depends on that index of refraction, which we call n, and that is dependent on the medium. Index of refraction describes optical density. In other words, how the photons are interacting with the mediums with the atoms in the medium. Now, here's just a list of common indices of refraction. These were all done with a specific kind of light that has a frequency of 5.09 times 10 to the 14th hertz. You can look up exactly what kind of electromagnetic wave that is because you have a handy-dandy pocket electromagnetic wave spectrum. Now, watch this. Woo! Super big. Notice air here is 1.00. That's technically a vacuum. Air is like 1.000037 or something like that. But air and a vacuum are very, very, very similar. Notice the diamond is super, super optically dense. That's one of the reasons why diamonds are super sparkly. Now, this is just kind of referring the index of refraction to the speed of light. Now, what a lot of people don't know is the speed of light is actually 3 times 10 to the 8th meters per second, because 3 times 10 to the 8th meters is how far light travels in 1 second. Now, in water, that's more optically dense, index of refraction of 1.33, light doesn't travel as far. In glass, index of refraction of 1.5, it doesn't travel as far. Now, this little guy right there, that's a diamond. That's what I just said. And light only travels 1.25 times 10 to the 8th meters. I know that's still really fast in 1 second, but comparing that to a vacuum or to air, it is more than 50% shorter. So that is crazy to think about that. So we can see this nice relationship. It is the fastest in air in a vacuum. It is the slowest in a diamond, which means as the refractive index goes up, the speed of light goes down. Now, actually, I'm just going to show this to you. This is a little bit confusing, this part of it, but Snell's law is, in general, this formula. N1 sine theta 1 equals N2 sine theta 2. So this side would be medium 1. This side would be medium 2. We're going to go through 2 examples. The first example is light passing from air to water. That's what we saw. Angle of incidence is 30 degrees. We want to know what the angle of refraction is. And I can tell you that N of water, that's here, N2 is 1.33. So there's my angle, there's my incident ray, there's my refracted ray. Angle of incidence, I'm looking for that angle of refraction. So now here we go very quickly. N of air is 1, N of water is the 1.33. I'm going to use Snell's law, N1 sine theta 1 equals N2 sine theta 2. This is all medium 1. This is all medium 2. So now I plug in 1.00 times the sine of 30 equals 1.33 times sine theta 2, so air and water. 1 times sine of 30 is 0.5. 1 times 0.5 is 0.5. I didn't do anything over there. Next step, I'm going to divide by 1.33. So 0.5 divided by 1.33 equals sine theta 2. So 0.5 divided by 1.33. Again, I can do that in 1 step, but here I did it in 2. Is 0.37594. The arc sine or inverse sine of that is theta 2. We get 22.1 degrees. That was an easy example. Now the harder example is this one. Again, you can pause to read this, but essentially I have an incident ray and I say it's going through zircon. That was something on that first list I showed you. Now, obviously, some light is always reflected. Like, again, we see color because of reflected light. So some light is always reflected. I don't care about that. This is actually here just to confuse you. I want to know if the light is incident at 21 degrees and how much is it refracted. And then I want to know when it gets out, how much does it bend away from the normal again. So incident into the zircon, out of the zircon. Now, for those of you that don't know, zircon is a fake diamond, cubic zirconian kind of thing. That's what that is. It is a much cheaper diamond, but it's a fake diamond. So we're going to do the same thing. Now I have one side and the other side. Here again, air going from air into the zircon, 1 to 1.92. That's my medium. I said it was coming into the zircon at 21 degrees. Here's my equation, n1 sine theta 1 equals n2 sine theta 2. I plug in all my stuff. 1 times sine of 21, that was there, equals zircon 1.92 times sine theta 2. 1 times sine of 21. Sine of 21 is 0.3584 times 1 is 0.3584 equals nothing happened over there. Divide 0.3584 divided by 1.92 equals sine of theta 2. Now I say theta 2 is equal to the inverse sine of 0.1867. So that's this guy right there, that math, which means the angle of refraction, theta 2, that guy, should be a smaller angle, it bent towards the normal, is 10.76 degrees. Now when I go from the zircon into the air, because it's allowed to pass through, N2 is what I just solved for. I'm going to go say 2 to 3. N2 is the zircon, 1.92. N3 is back into the air. That was on the bottom of that picture. So N3 is into the air. Theta 2, I just figured it out, 10.76 degrees. 10.76 degrees. I want to know what, I didn't write it down, sorry. I want to know what theta 3 was, that guy. The angle of refraction outside of the zircon. So there's my equation again. It looks just exactly the same, except now I'm going from 2 to 3. 1.92 times sine 1.92 times the sine of 10.76 degrees equals 1, that's the air, times sine theta 3. I don't know that. Now, 0.35, hey, look, that number looks really close to that number. That's interesting. Equals 1 times sine theta 3. If I divide 0.3585 divided by 1 sine theta 3, so divide both sides by 1, I get that 0.3585. So now I just take the inverse sine to get what theta 3 is. That gets rid of my sine. And I get 21 degrees! What does that mean? Look. Theta 1, 21 degrees. Theta 3, 21 degrees. What exactly does that mean? I'm going to go all the way back to this picture. Light has no memory. It's a beam of light. It has no idea that this thing is here. It's just trying to travel. It's traveling at 3 times 10 to the 8th meters per second in the air. It's traveling at 3 times 10 to the 8th meters per second in the air, or 186,000 miles per second, which means whatever this angle is, it's the same angle. Those two rays are parallel to each other. They travel, they get bent in and bent out. It's the same exact thing. Hopefully that made some sense to you. And I'm going to leave you with this one last question. And this one's an easy question. You should already know the answer to this. I haven't even asked the question yet. Ready? A boy shines a flashlight underwater as shown in this picture. Ready? Well, we want to know the correct path of the light. And there is my creepy boy. How creepy is that kid? That kid is really creepy looking. I don't know what's happening. So he's underwater and he is shining a light above the water. This goes on to what's coming next. Total internal reflection. Really cool. Anyway, so when he shines it, is it going to bend away? Is it going to bend like that? Is it going to go right straight out of the water? Or is it going to go towards the surface of the water at Z? Got to think. Got to imagine the normal line here. And it's going from a thick to a thin, thick optical density or index of refraction to a smaller. So it's going to bend away from the normal. And the normal, well, X is towards the normal. It's got to be Z, away from the normal. Am I right? Yes, I am right. And that is all I have for you today on reflection and refraction. It was a little bit long, but it wasn't super long, and I was as entertaining as I always am. Please, if you are watching this on YouTube, feel free to like, click, or subscribe, and you will see me next time. Hathead. Haven't had a haircut in like 4 months. Later.